All right, somebody give me a ping, please. Let me know if you can hear me.
Yep, I can
Awesome.
hear you.
Great, thank you. All right, well, so this is our last class. And so, first of all, congratulations to everybody who stuck it out this far. This is, one of the harder classes in the entire engineering computer science sequence. It covers so much material, so many different topics, and it builds so viciously on itself that, if you miss the first lecture on product of sums versus sum of products, then nothing else in the course will make sense. Because we keep coming back to that when we do K-maps, and if you miss the K-maps, then when we do state machines, the simplification doesn't make sense, and it's this Jenga block assembly of things, and if one piece is missing, it can be brutal to try to catch up. So congratulations on sticking this out, and I feel like most people have gotten the essential material that they need out of this course. Um, this course is very different from Engineering 270. So 270 is a microprocessor class. We do not do Verilog. We do not design machines with flip-flops. We do not make state transition tables. We don't do product of sums. We barely write a truth table. So when you're done with 250, you're done with sort of this subject area in some sense. But the things that we've done in here, I feel, and I've been told by former students, kind of form the foundation for everything else that comes, at least in the computer science curriculum. All of the programming courses, when we dig more into C programming, data structures, computer architecture, all of that stuff is sort of built on the foundation of Engineering 250 and later CSE 215 if your CS sequence. That course comes up in your final year. So this is an important course, and it's good stuff. And the points in this course that are most critical will come up again and again, and they'll be used in other things, and so those will get reinforced over time. Verilog, for example, is not going to come up again unless you're electrical engineering and you go into maybe an embedded system track or something like that. But it will still be there in the back of your mind when you're doing other things. Boolean algebra will be there forever, right? That's going to be there every time you write an if statement in a programming class, and you need to figure out, should I do an and or an or and a not or a true, and you're in your subconscious using De Morgan's theorem to figure out how to write your if statement, right? This stuff will come back. So my plan for today was to talk a little bit about Verilog on the homework in the lab, and just kind of make a few comments on that, and then just sort of go over the review topics on Canvas for the final exam and talk about logistics for the final. I have not updated the review topics on there, so we'll go through those, and if there's something we haven't talked about, we'll take it out, and if there's something that we haven't put on there that we think of along the way, I'll put it in there. But it's a basic list of what we usually go over in this course. But we'll narrow that down, and we can go through topic by topic from the beginning. But let's start with questions. If there's anything that you want to ask about or go over, let's begin with that, and then fill in the other stuff at the end. All right. Well, let's go on to look at the homework and the lab, and mainly, well, let's look at the lab first. And most people nailed this. This was great. So the first experiment is an even parity generator. And a few people, I think, misinterpreted this and tried to write a circuit, tried to build a circuit that would tell you whether you had an even number or not. And so if you have a number like this, if you want to know if it's an even number, you can just check that least significant bit. And if it's a 0, it's even. If it's 1, it's odd. And so you can generate a 1 or 0 to say this is an even number or an odd number by just looking at that bit. And so some people did that. But that's not what a parity generator is. A parity generator is saying, hey, let's see how many 1s or 0s we have in our number. And let's see if it's an even number or an odd number. So this circuit is saying output a 1 if there are an even number of 1s. So output 1 if there's an even number of 1s, 0 if there's an odd number of 1s. And that might be a peculiar thing to do, but you can think about the effect of it as follows. So you're going to take this 8-bit number, if you were to append a 9th bit, x, and that 9th bit is set up like this, the result is, if in here you have an even number of 1s, you're going to add another 1, you're going to end up with an odd number of 1s. So the total number of 1s in these 9 bits will be odd. And if these 8 bits contained an odd number of 1s to begin with, then the output bit is going to be a 0, and adding a 0 is not going to give you another 1, so the total number of 1s in this 9-bit number is again going to be odd. So a parity generator like this will have the following behavior. You feed in an 8-bit number, you take the output of your circuit and you add that as a 9th bit. And now you have a 9-bit number and you're guaranteed the total number of 1s in that number should be odd. Okay, that's what the parity bit is for. So the parity bit lets somebody who receives this number look at it and immediately know if a single bit got changed somewhere. So right now we have this number 11010110. We have 1, 2, 3, 4, 5 1s. So our parity bit would be a 0. And if I was sending this 8-bit number, I would actually transmit this 9-bit number with this extra 0 at the end, which we call the parity bit. And so if I tell you this number and you write it down and you look and you see an odd number of 1s, you have a certain level of confidence that you wrote the number down correctly. But if you wrote down the number like this, you could look at it and say, how many 1s do I have? 1, 2, 3, 4. That's an even number. Hey, there's a mistake. This should not be the number that you gave me. And you could say, tell me that number again. And I'd read it back to you more slowly and you'd write it down correctly. And then you could say, oh, there's an odd number of 1s. Okay, I got it. Good. So your circuit was supposed to generate this kind of behavior. And the way we talked about this last time was you can do this by using exclusive ORs. So if you have a number like 0, 0 or 1, 1, your output should be, these are an even number of 1s, your output should be a 1. And if it's a 0, 1 or a 1, 0, your output should be a 0. And so this was an exclusive OR complemented. And if you continue that chain of thought, what you find is that the way to generate the entire signal is to XOR all 8 bits and then negate that. And so the waveform you get looks kind of strange. It's not the usual repeating pattern that your clock is. And so this looks like something like that. And then it kind of repeats, but it gets more drawn out in the next bit, and so on and so forth. Alright, so that was experiment 1, and it's an assign statement. So you can say something like, assign x equals negate a bracket 0 XOR a bracket 1 XOR a bracket 7. There are other ways to do this, right? But this will work. There are shortcuts you can use that a number of students used. One student referenced the shortcut and said, hey, I found this on such and such a site, and this seemed easier than writing out all 8 of these terms with all these XORs in the middle. That's fine. But you want to make sure you understand anything that you do like this. And for example, if you're in a job interview and someone asks you, to write some Verilog code on the board, and you write something down, you want to feel pretty good like you understand what you're writing. And if there's a different way to do this that makes more sense to you but might be longer, I think that's a better way to go, right? Because like a job interview, you write something down, someone's next question is going to be kind of like, tell me about this, or why did you do this, or what would happen if you didn't do that. And so I'm generally a fan of doing things in a way that makes really, really good sense to you. Even if it doesn't feel particularly elegant, even if your solution might end up being, twice as long as somebody else's, that's okay, right? This is a learning environment. And so the Verilog that I'll write generally won't be very fancy, right? It will be things that could be done differently, but I want to understand really well what exactly I'm doing. So experiment 2, 8-bit up-down synchronous binary counter using Verilog. The other one burned out this morning too. Yeah. And so we talked about this a little also, but system diagram. There's a clock. There's maybe our up signal. There's our output. And here's a reset. And we could do this like so write your usual module code, but our always block could be something like this. Always at positive edge clock. And I'm gonna assume that we've set up a module and we've defined clock and reset and up to be inputs and out to be an 8-bit output, and out is the only thing that has to be a register. Everything else can be a wire. So always at positive edge clock begin, and you can say if reset out is assigned 0, else if up out is assigned out plus 1, else out is assigned out minus 1. And that says all of these things happen simultaneously, right? Since these are else's, exactly one of these 3 statements is going to fire, possibly. So if the reset signal is asserted, then the output is set to 0. And you don't need to do, 8 single quote D0 or something like that. The language will understand, 0 means, in this case, all 8 bits should be set to 0. Otherwise, if our up signal is asserted, well, this implies reset is not asserted, because if reset was asserted, this statement would be true. So if we come down here to the else, it means reset is not asserted. So if up is asserted, then set out equal to out plus 1. And since out is an 8-bit register, if you count up to 255, which looks like this, well, we would come up with 256 in binary. We would come up with 8 zeros with a carry out of 1. But since it's an 8-bit register, this carry doesn't go anywhere. This ends up just being 0. And as an 8-bit number, 256 is the same as 0. So we don't need to say if out is equal to 255, set out to 0. this will happen automatically. And similarly, if out is equal to 0 and we subtract 1, it will become 255, 8 ones. Now you can code that explicitly, and the compiler will probably just ignore that extra statement, because a good compiler will be smart enough to know, oh, I'm going to do exactly what would happen anyway if I just, said add 1 or subtract 1. So it doesn't hurt to put in that extra statement. And again, if that makes it clearer to you, if that really nails down for you what's going to happen when it rolls over, go ahead and do that. All right, the shift register I think everybody got, which is great, because this is one of the more complex circuits, and we went through this in a fair amount of detail last time, but the main key, remember, was you make a register of 16 bits. Let me just call it D. And in your always block, we can do something like, D bracket 0 is loaded from in, D bracket 1 is loaded from D0. D15 is loaded from D14. And then you have options. You can say out is assigned from D15 if out is a register, or you could make out a wire and use an assign statement and say assign out equals D15. The big thing to remember here is that Verilog, all of these statements fire at the same moment. And this is like our state machine circuits, where we have a series of flip-flops, but they're all fed from the same clock. So at the moment that, the positive edge of the clock hits, or whatever our always statement is, at that moment, this happens, this happens, this happens, this happens. So the current value of D0 is being loaded into here at the same moment that the value of D0 is changing to in. So in does not get loaded into here and then loaded into D1. In goes into D0. What was in D0 goes into D1, and so on. And I could write these 17 statements in any order I want, and it's not going to affect the circuit, because it's just 17 flip-flops with their clocks connected together. And then in question 4, the 5 of 16 counter, so that's really taking your shift register circuit, and you can do something like assign. And you can assign whatever you called your final output, your 5 of 16 detector. So assign X equal, and the trick we suggested was just add these together. And if it's equal to 5, set your output equal to 1, otherwise set your output equal to 0. Alright, so those are the experiments. I saw a bunch of cool new experiments, so that was good. And we are done with labs for Engineering 250, so that's awesome. So Engineering 270, we have several labs in that course also. Yay! Those will be different in feel. We generally won't be using Tinkercad. We'll be using a tool designed specifically for the microprocessor that we study in that course, something called MP Lab, which works with a PIC chip. It's a particular type of microprocessor. But the structure of the labs will be very similar, right? So you'll have a series of experiments. You'll have to write up the experiments. There'll be a requirement for a new experiment at the end, lessons learned, all of that kind of stuff. Are the Engineering 270 labs group-based for your summer in person? I have not decided for sure, but my expectation right now is that Even though the 270 lectures will be in person, the labs will continue to be done remotely, individually. And we got a few weeks left to decide on that, but I don't feel comfortable telling students that they have to work in person in groups in a closed room in the STEM building all summer. To me personally, that doesn't feel good. So, so the labs will probably be online, but it's a relatively minor difference in experience compared to 250. 250 in person, we'd really be pulling boards out of a box and putting wires in and components, and you know, smoke would be coming out when we hook the power up backwards and things like that. 270, so much of the work is done in the simulation anyway, because once you have the physical microprocessor and you load the code in, there's not a whole lot of debugging you can do. And so if it works, great. If not, you're kind of back to the drawing board in the simulation. So even in an in-person lab setting, we'd be spending a lot of time in front of a computer running the software. So, and there's no Verilog in 270. So that's something people usually like to know. Alright, so let me pull up the homework. Alright, so homework. Hey, good morning. All right, so mostly I looked at question 2. Question 1 is an assign statement, right? So assign f equals, and it's, you know, tilde a, ampersand b, ampersand tilde c, pipe, tilde a, ampersand b, ampersand c, pipe, a, ampersand tilde b. So this one is almost exactly like this, right? With different particulars in the assign statement. And I kind of brushed over that one and made sure people did it, and it looked nominal, but I didn't dig into that one in detail. 2 I looked at more closely. So 2, you're trying to implement a positive edge triggered T-latch, and as I mentioned in the textbook, sometimes the words latch and flip flop get used interchangeably. But a T flip flop or a T latch in this case has this following behavior. Right, if T is 0, your output should not change. If T is 1, your output should toggle. So it's a unit like this. T goes in, Q comes out, and there's a clock. And so we could code that always at positive edge of the clock begin. And there's really only one thing to check, which is what's the value of T. So if T equals 0, then we don't need to do anything. So really all I care about is if T is equal to 1, then Q is assigned to not Q. And in Verilog, like in C, we could just say if T, and this means if T is non-zero, then set Q equal to not Q. And that should give you a T flip-flop. There's no reset line on here, and so if we try to simulate this, since Q does not have an initial value, if we complement it, it's still going to have an undefined value. So we could add a reset statement in here. So if reset, then set Q equal to 0, else If t equals 1, set q equal to not q. So now we've added a synchronous reset so that if this line is high when the clock ticks, the output goes to 0. And then some people did the following. They added an additional output, which was called q bar. And in here I could set q bar equal to not q bar, and in the reset I could set q bar equal to 1. And now this is the opposite of q. But you also have the option of, after your always block, doing just a plain assign statement. Assign q bar equal to not q. I switched from an uppercase to a lowercase. Not q. And so this is defining a flip-flop, right, that does all of this stuff. And this is saying, hey, let's take the output of this flip-flop, run it through an inverter, and call that q bar. And the effect of somebody using this circuit is, oh, this is just a T flip-flop with a Q and a Q bar output. What would the circuit actually synthesize to? I don't know. It depends on the compiler, it depends on the synthesizer, and so on. But the effect should be the same as, you know, a plain old T flip-flop with a pair of outputs, true and complemented. But that wasn't asked for in the problem, so you didn't need that. You want to make sure your flip-flops have memory. And so if you do something like that, you're not using the old value of Q to set the new value. That's kind of a giveaway that you're not remembering something, right? And a flip-flop, it's a sequential circuit. It has memory to it. The output sometimes depends on the previous value of the output. In fact, for a T flip-flop, it always depends on the previous value of the output. And so you want to make sure your circuit has some kind of memory. And this is tricky to test sometimes, right? How do you generate a set of waveforms to know what your circuit is doing? So you might want to take your reset signal and start off by driving that high. So have it go low for a few clock cycles and then stay low, have it go high and then stay low for the rest. Your clock is just this fast pulse train. And how fast do you make the clock? Well, I don't know how fast the circuitry can run in this simulation. I wouldn't make this a 1 nanosecond clock because, you know, we've looked at data sheets and we know that, you know, an AND gate sometimes takes 4 or 5 nanoseconds. But if you make this, you know, 40 or 50 nanoseconds, that's usually plenty of time. The default is 100. There's nothing wrong with doing 100 nanoseconds for your clock. You have to squish your display up a little more to see your waveform. But, you know, you set it to some time that seems reasonable. If your circuit was not behaving correctly and you were pretty sure it was right, maybe your clock is too fast. And, you know, if you're bored and you miss Verilog sometime during the summer, you could come back to this tool and you could do some experiments and say, hey, let's take that 8-bit up-down counter I had and let's try to clock it with a 1/4 of a nanosecond clock and see if it still actually counts. And at some point it should break, right? Because the simulator should understand about propagation delays, or maybe not. So, you know, some nominal clock that's repeating, drive your reset line in the beginning, and this is a T flip-flop, so what should we do? Let's set our toggle input low, and then let's set it high for a bit. But let's do this in a way so that the next time we set it low, our output's going to have the opposite value. In other words, we don't always want T to be low while Q itself is 0. Sometimes we want to set T to be low when Q is 0. Sometimes we want it to be low when Q is 1. And so you need to kind of design your experiments in a way that test all of the behaviors of your circuit. And if you say something like set Q equal to T, well, you might luck out, and you might say, you know, hey, I raised T and Q went high, and then I dropped T at the next clock cycle and Q went low. So coming up with these waveforms is part of the trick of knowing how to design a circuit and test it and use it. All right, so that was the positive edge triggered T latch. And then positive edge triggered SR flip flop. So, and I think we talked about this one in a little bit of detail last time, but our usual always block. So let's have a reset line. If reset, Q becomes a 0. Else, so what does an SR flip-flop do? So if both S and R are 0, it does nothing. Doesn't change the value. If R is a 1 and S is a 0, it resets, so it changes the output to a 0. If S is a 1 and R is 0, it sets, which changes the output to 1. And if both of these are 1, I don't know what we want to do. We've got a few options. We could say this is undefined, and we could simply not specify a behavior. Or we could say set is dominant, and so we'll pay attention to that 1 in S and make the output a 1. Or we could say the reset takes precedence, and that 1 in the R will force this to a 0. Or we could do what a JK device does and say, hey, we're going to toggle the output. But you know, you got to decide what you want it to do, or you know, just say, hey, this is undefined. So let's just worry about these three pieces up here. How could we code this? Well, we don't need to do anything for S is 0 and R is 0, because the behavior there is don't change anything. So I don't need a statement for that. So I could code these up very explicitly, and I could say if not S. Well, let's be explicit about this. So if S equals 0 and R equals 1, then let's set Q to a 0. Else if S equals 1 and R equals 0, let's set Q to a 1. That's the set state. And I could leave it right there. And then if both of these were 1, it would be a no op. It would just leave Q at whatever value it is. And that could be my whole flip-flop definition. But again, you can experiment with this, right? Do I have to say S equals 0, or could I just say if tilde S? If tilde S ampersand R. If S ampersand tilde R. Do I need parentheses? I don't know. Experiment, right? What if I don't put these parentheses here? Does the equality take precedence over the ampersand? So you've got a few options here, right? You could let me lecture on this and tell you how this works. Well, that's not very interesting, right? And not critical, because we know we can use parentheses, and so we have a way to do this, right? You could try to read about it. Well, that's going to be a lot of reading, because Verilog is this big topic. And if you try to watch, you know, a 2-hour YouTube video to find out whether you can say, you know, tilde S instead of S equals 0, that's a lot of video watching, right? Or you can just try it and see what it does, right? You could come up with your own experiment that says, hey, you know, let me just do some different logical conditions in here, and I'll generate one signal using this approach, and I'll generate the other signal using something like this. And I'll generate a third signal using something like this, without parentheses. And I'll randomize S and R, and I'll run this for, you know, 100,000 nanoseconds, and I'll just look at the waveforms. And if my output waveforms are all the same, that's an experimental validation that, hey, these are probably doing the same thing. And if this waveform comes out different, it's like, oh, this is not the same as this. Okay, maybe the ampersand is being done first, and then the tilde is happening. And then I could dig into that. So, you know, these aren't things that you would normally do as part of Engineering 250, but like I say, if you were bored, if you had nothing else going on in your life except this lab or this homework, these are things that you could do. And if this was your gig, if this was what you wanted to do for a living, right, you can learn a lot about this by working with the tool itself, by digging into it. And I'm mentioning this because a number of you are moving, you know, through the computer science track, and this is going to be a common theme in your 200 level programming courses, where we will learn one way through a problem, but it's really just one particular path, and there are so many other ways to get to a solution. And the best learning you're going to get is the learning that you get by doing experiments on your own. Bye, have a good day. All right, see you this afternoon. The best experience you're going to have for learning these concepts is going to be to get in there and get your hands dirty and do these what if kind of experiments, you know. So I wrote this, but I thought I could write it this other way. Well, go ahead and write it the other way and see what happens. And I think it's very similar in the engineering track. If you're doing Engineering 204, 52, 53, there's so many different ways you can design a circuit, and you'll probably see a particular way to do it in class, but, you know, maybe it occurs to you, oh, I would have done that differently. Go ahead and do it differently and see what happens. So that's all kind of like preamble, pep talk, something to keep in the back of your mind maybe for courses coming up in the future. So that was a little sidebar. But you'll hear me talk about this a lot if you're in the CS track. All right, 4-bit binary down counter. So, you know, you did an 8-bit up-down counter in the lab, so this is a simpler version. It's only 4 bits, and it always counts down. So that's very straightforward after the lab. 3-bit binary to 8-line decoder. So I did not dig too much into 5 and 6 because there's potential confusion about what it's even asking for. I did dig into 4 and 3 and 2. But let me just mention 5 and 6. So the 3 to 8 decoder, so we have 3 inputs going in, and that works like a select line. Hold on one sec. So we have a select line, we have an input, and then we have a series of outputs.
Professor,
Yeah.
we are still seeing the homework 7.
Thank you.
Writing something else.
Thank you. So we have a 3-bit select line, we have an input, and we have 8 outputs. So out 0, out 1, out 7. And so this select chooses which of these outputs should be driven from the input. And so this is a combinational circuit. There does not need to be any memory, so we can just use a series of assign statements. And for example, out should be equal to the input if your select is 0. So we could say assign out bracket 0 equals if select is equal to 0, set out 0 equal to the input, Otherwise, set it to, and does it say what this is? This is active high. So set it equal to 0 if it's not the selected output. Otherwise, set it equal to the input. And then assign out 1 to be if select is equal to 1. Set out 1 to be the input. Otherwise, set it to 0. And then out bracket 7 should be if select is equal to 7, the input. Otherwise, it should be equal to 0. And now the behavior is 7 of these outputs are guaranteed to be 0. One of them will be a copy of in. And if in happens to be 0, then all 8 outputs will be 0. But if in happens to be 1, one of these outputs will be equal to 1. Which output? That's determined by this select input. So select is a value from 0 through 7 that chooses which output from 0 through 7 is a copy of the input. Alright, so that's the decoder or demultiplexer. And then the encoder, the main encoder we talked about was, well, there's a couple of encoders. There's a 8 to 3 encoder. There's a priority encoder. I think most people took this to be a priority encoder, which was how I took it. And so in the textbook we had this section on the 74148. And the idea was this circuit tells you the input with the highest priority that is active. So this is an active low circuit. So active means the input should be a low. And so if input 7 is low, we want to say, hey, input 7 is the one that had highest priority with a low value. And since this is active low, we output a 7 as 3 zeros instead of 3 ones. So there's lots of negative logic here. Let's ignore that and let's just treat this as a plain old active high circuit for the sake of thinking about the Verilog. So the behavior might be like this. So we have input 0, 1, 2, input 6, input 7, and our output. And this is active high. So if this bit is a 1, we want our output to be a 7. If this bit, which is 111, if this bit is a 0 but this bit is a 1, we want our output to be a 6. If these two bits are 0 but this bit is a 1, then we want our output to be a 5, because this was input 5, and so on. If we put in 0 down here, then this would be 0, 1, 2, and so on. If we make it active low, then this would be, the 1s and 0s would get swapped. And if we make the outputs active low, the 1s and 0s would get swapped. But the overall behavior is, right, this circuit looks at these inputs as having different priorities. And the highest priority input with a 1, that's what this output reflects. And so however you construct the truth table, you can write Verilog code accordingly. And one way to do this is with a series of assign statements. So if we have some output 2, 1, 0, so a 3-bit output register, we could say something like, let's just say assign out equals if input 7 is a 1, then let's set output equal to a 7. right? So if this bit is a 1, that's all we need to know. The output should be set equal to 7. Otherwise, let's set it equal to the value that we should get if we have one of these input combinations. So let's make a 6-bit priority encoder that outputs a number from 6 down to 0 based on these 7 bits. And so how would I do that? Well, I'd say if bit bracket 6 is asserted, let's set our output equal to 6. Otherwise, let's set it equal to the output of a 5-bit encoder. So if in bracket 5 is asserted, let's set the output equal to 5. Otherwise, set it equal to. And so we have these nested ternary operators. And so all of this is the else clause, right? If in 7 is 1, set output equal to 7. Otherwise, set output equal to all of this stuff. And all of this stuff says if input 6 is asserted, set the output to 6. Otherwise, set it equal to all of this stuff. And so that's one way to build this circuit. A more straightforward kind of sum of products, product of sums approach would be to maybe look at each bit of this and say, assign out bracket 0. So this least significant bit to be in 7 or not in 7 and not in 6 and in 5. So this third row down here. Or not in 7, not in 6, not in 5, not in 4, and in 3. Or not blah, 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 or in 1. And just, basically write out the conditions under which you want this least significant bit to be a 1. And then do the same thing for out bracket 1, and then do the same thing for out bracket 2. And out bracket 2 is a simpler expression. It's going to be equal to 1 if these 4 bits are all 0. Then you're guaranteed this bit's going to be a 1. So that's a way to kind of look at the truth table and do something more directly from the truth table bits. A third way to do this is to, if you use an always block, you can say always when any of these inputs change, or you can say always asterisk to say always, always. And we didn't go over those, but that's a third approach. A fourth approach is to make this a clocked circuit, and that's usually not something that's done. You don't usually see encoders with a clock. But if you put a clock in, then you could say, always at the clock edge, and now you could write a series of if statements. If in 7 equals 1, then output equals 7. Else, if in 6 equals 1, which means in 7 must have been a 0, then output equals 6. Else, if in 5 equals 1, and the only way that if is going to be executed is if also in 6 was 0 and in 7 was 0. So if in 5 equals 1, then out equals 5. Else, and so on. And so you write, an 8-part if then else statement, and that would work. And that actually parallels the structure of this. If you take this ternary operator and you break it into a series of if then else's, it ends up being exactly the same as what you might code in an always block. So lots of options there. Alright, question 8, we basically wrote out the code for that in the previous class. Let's talk about question 7. And so 7 and 8 I basically looked at, and I looked to see that you made an attempt on it. And I think I warned people I was going to grade those very gently. So if you made a stab at it, you mostly got credit, and pretty minimal deductions if there were issues. But let's just take a look at a solution for a traffic light. And let me see if I can find this. So I think this was a version I simulated and it works. So traffic light controller. So Verilog, you can also do comments in the old C style of a slash star followed by a bunch of stuff followed by a star slash. So all of the stuff up here is just comment. So there's our three-way intersection. Here's the 6 states we talked about last time. So we're looking at which light is green or which light is yellow. And at any point in time, exactly one light's green or one light's yellow. All the other lights are red. So we only need to know which light's green or which light is yellow. And then here's a simplified transition table based on your present state and your 3 inputs. What's your next state? But I've also got a notion of a next state. So I'm thinking of changing states every 2 seconds. And next state tells me what state should I be the next time, and then what state should I go into after that. So for example, if west is green and there's no cars anywhere, my next state is still west green. If west is green and there's a car to the east, east has priority, and my next state should be west goes yellow, and the state following that should be east goes green. And if west is green and there's a car to the south, then my next state should be, hey, west goes yellow and then south goes green. And if there's a car to the south and the east, my next state is west goes yellow, and then the following state will be east green. And so I wrote these out, but we don't really need to be this explicit in the code. And then there's a general case. If you're in any yellow state, I'm ignoring which cars are present, and my next state's going to be whatever I said my next state was going to be. So in the case of a yellow light as my present state, I just go to whatever I specified in this next state. And so there's the module definition. There's a clock, a reset input, 3 car sensors, and I made these active low for a reason, because I used to have a test bed platform that students could use to actually, move around little toy cars on an intersection, and a light in the middle that would change colors. And the sensors were set up to be active low. They were magnetic sensors. These cars had magnets on the bottom. So active low, and then the 9 outputs here. And then parameter is a keyword we can use in Verilog to say this symbol WG is a replacement for the number 1. This symbol SG is a replacement for the number 2. So it's like a pound define statement in C if you've done C. It's not a variable or a wire or a register. It's just a compiler trick that says, hey, anytime you see SY, I mean the number 5. And so I can say, if my current state is south yellow SY, instead of remembering that that's, state 5. So I inverted my car sensors because I said they were active low, but I wanted to write this code thinking of active high. And I said in the assignment that we had a clock that toggled every half second, but when I wrote this code, I was using a clock that toggled much more quickly. So this is just a counter that resets every, I think 15 million ticks, and I use that to toggle a slow clock. So clock could be the half, the 2 hertz clock that's coming into your circuit. And then here's the state machine. So at the positive edge of the clock begin, if there's a reset, I just set my state to 1. And that's just a default, startup case. Otherwise, let's look at the state. So if we're in state west green and there's a car to the east or the south, we want green to go yellow, and we want our next state to be either east green or south green, depending on whether there's a car to the east. If there's a south green light right now, the only situation we care about is if there's a car to the east, or there's a car to the west and no car to the south. So if there's a car to the east, same thing. Change into the south yellow state, and then after that we're going to go to east green. Otherwise, if there's a car to the west and there's no longer a car to the south, so south is green, there's no car in the south, but there's a car to the west, right? And we know since we're down here that east is also 0. Then go to the south yellow and prepare to go to west green after that. And then east green, the only situation we care about is if east is green. If there's no car to the east, we may want to change the light. We're going to do that if there's a car to the west or the south. So if there's a car to the west or the south, we're going to change east to yellow. And then our new state after that's going to be either west green or south green, depending on whether or not there's a car to the south. And then in the 3 yellow states, we just set our state to be whatever we said the next state was going to be. And that's the whole state machine piece of the traffic light controller. And then here's the 9 assign statements that set up the 9 lights based on the current state. So west green is just a 1 or a 0 based on whether your state is west green. West yellow is the same. West red is assigned to be 1 if we're not in west green and we're not in west yellow. So I could write logic statements in here also, or I can write them out explicitly like this. And that's the whole traffic light controller. So those, 7 or 8 or 9 proto boards that you used in Lab 6 to build the traffic light controller basically come down to this much code. Actually, it's just this much code. Right? So that's what Verilog is bringing to the show. The ability to take, not just, the circuit that you had to build on several proto boards, but all of the analysis you had to do to get there. The insight of, delayed green versus old delayed green. The Lab 3 circuit that you had to design and come up with a circuit diagram for and test and so on and so forth. All of that came to bear in your final circuit for Lab 6, right? Verilog, it's a page of code. And this is much more flexible. For example, to say that I wanted my sensors to output a 0 when a car was present, all I had to do was add these 4 statements. If I wanted to change what the delay was, I could just change, how often I trigger my clock signal based on whatever the actual clock is going into the system. So this is what hardware definition languages are for, right? The argument for why we spend most of the course doing this the long way is that unless you understand, what a state machine is, unless you understand what minimizing a truth table is all about, you can't really make efficient use of a hardware definition language, right? You've got to know what your target is, what you're trying to build, what kind of synthesis outcome you want, before you can effectively think in terms of, okay, well, I'll do something like this. So I think I've given you this analysis before, right? This analogy before. It's like in calculus. You spend all this time studying, f of x plus delta x minus f of x divided by delta x. And you take the limit and you spend all this time studying limits first so you can do limits. And you do all of these polynomial evaluations of x plus delta x squared and so on and so forth. And then, after you've done through all of that, you get this rule that says, the derivative of x to the n is just n times x to the n minus 1. And it's like, why didn't you just tell me that day one, Why'd we spend, 3 weeks doing epsilon delta stuff? Well, because the epsilon delta stuff helps you understand what it means when you say the derivative of x to the n is n times x to the n minus 1. So the flip-flop work and the sum of products and product of sums and all that helps you understand what's going on when we say something like always at positive edge clock. If reset, then set state equal to 1. And if you can visualize that as a piece of circuitry where we have a reset signal that's being fed from the output of some kind of combinational logic that takes state and tells you if it's equal to 1. So, checks to see if bit 0 is a 1 and bits 1 and 2 are a 0, so run them through inverters, AND them, and so on, right? Then you can make sense of and write Verilog code that'll work well like this. So that's in there, partially just as another exercise to work on, but also partially as a way to kind of see, what Verilog can unlock in terms of capability. All right, and then 8, like I said, we went through that in detail last time. That's 3 assigned statements. So if function equals 0, or assign, well, I'll just do it. So assign out equals, and we could say function equals 0. So if function is 0, we're going to set output equal to a plus b. Otherwise, we're going to set it equal to the following. If function equals 1, let's set it to a minus b. Otherwise, let's set it to a times b. And I think I matched my parentheses. So it's a fancy way of saying if function equals 0, do a plus b, else if function equals 1, do a minus b, else do a plus a times b. All right, so any questions on all of that or any of that? So good chance for a Verilog question on the exam. A Verilog question like one of these earlier homework questions, not a Verilog question like, question 7. Low-hanging fruit, right? So you've got 12 single-sided pages of notes available for the exam. I think we'll look at the exam in a few minutes. But if you don't remember exactly how this gets spelled out, on your note sheet, put down a little piece of Verilog code. Just write down a module with an always block and a register definition and maybe an assign statement, and that helps you remember. Do I put a semicolon here? Does the ampersand go inside or outside the parentheses, right? And if I'm grading a Verilog question on the exam and you forget a semicolon, I'm not going to take off points for that, because that's what compilers are for. But the more confident you are in writing something, the more likely you are to get it right. Right? Confidence is a big part of it. So an easy way to do that is just write down some sample code to draw from. How many questions on the exam? I have not the slightest idea. It's going to be a 2-hour exam. And I don't know, several questions, maybe 10 questions. Oh, did I freeze? I'm moving. Your internet connection is unstable. I'm back. Okay. Went into phase space for a minute. I don't know how many questions yet because I haven't written the exam. Several questions, maybe up to 10 questions. It's going to be an hour and 50 minutes for the exam. So something that will take a good chunk of that, but hopefully not leave you racing the clock, down to the last second. So I'll shoot for about an hour and a half exam, and you'll have an hour 50 minutes for it. But let's take a short break, and then let's just kind of talk about general topics that we've gone over and types of questions you'll see on the exam likely. So let's do a short break, and let's come back at about 5.5 minutes. All right, so I'll see you back in a few. right. Well, let's take a look at the final. So your final exam should be on Monday, and it's during regular class time, so it's 8 o'clock to 9:50 a.m. And it will be the same setup as before. So you'll read the questions and write out the answers, and then upload those as a PDF. So yeah, it can take some time to scan and upload. So nail down that process. And if you don't have a good process, right, we've got 3 hours of lab hours tonight. We got office hours Thursday morning. We got office hours Friday morning. I'm kind of anticipating that to be a lot of dead time. So that's 6.5 hours of time that we can screen share and look at your tool set and look at how you're scanning and how you're saving as a PDF and so on, and really nail that down. And those are useful skills down the road as well, probably. And there's lots of different ways to do this. So if you're not sure how to do that efficiently, or if you feel like that's taking 20% of your available exam time, come by and let's look at your tool chain and see if we can make it more efficient. Ideally, you can be uploading the exam as you go. So, open up a Word doc or a Google doc or a LibreOffice doc or an OpenOffice doc, or, some kind of document. And as you finish writing a page, scan it, drag it into your document, and have this building document as you go, right? Control S to save it on the way. And maybe, at the 1 hour point and the hour-and-a-half point, just hit the export button. Export as a PDF, and then upload that to Canvas. But have Canvas open ahead of time. Have your tools open ahead of time. Have folders open where things are going to get saved ahead of time. If your scanner always puts your scans into a certain directory, have a folder open in that directory so that you're not spending your time, hunting and pecking with the mouse, saying, okay, let's go to, users/myname/documents/scans, set this up ahead of time so that it's as streamlined as possible. And this is another mantra that you'll hear me talk about in programming courses again and again and again. Do not let your computer get in your way, right? Your computer is a tool, and it should be a tool that helps you do things that you need to do quicker and easier and more efficiently. And the experience out of the box is not that. The PC that you buy and bring home is not designed to make you more efficient or make your life easier. It's designed to get your money, right? And the tools that you find on there are not designed to increase your productivity. They're designed to get your money. And one way that happens is by changing things across time. So the way you used to do something, 2 years ago in Word might be different today. Why? Because now you have to buy a new version of Word to keep up with what everybody else is doing, and this gets more of your money. So take back your computer, right? Take back ownership of your computer and make it your tool that works the way that is most efficient for you. And I harp on this in my 200 level CSE classes, because those classes spend so much time. They force you to spend so much time in front of your computer. And if you're spending time, going through menus to open up your editor, that is a waste of your time. And if you're going to spend your life editing code and compiling code, and you spend 1% of that time going through a menu bar, right, that's a lot of time. So this is an opportunity to maybe shift gears if you haven't done this before, and really kind of take back ownership of your experience when you use your computer, and try to make it work for you, instead of hey, here's some commercial for something that you could you could buy that will, take more of your money and give it to someone else. Let it be a tool, right? If you had a screwdriver that displayed a pop-up and said, would you like to buy some real estate, every time that you wanted to use your screwdriver, you'd throw the screwdriver away. So that's a bit of a personal rant, obviously, but come by and we can look at how you're doing this and see if there's ways to make it more efficient, so that hopefully, this is kind of a, while it's scanning my document, I'm working on the next problem kind of situation. You'll reload Canvas right around 8 o'clock, and I'll have the exam posted. It'll open automatically on Canvas at 8. It will be a PDF you can download with a series of questions. Write up your answers, scan them, submit the PDF. You can submit multiple times, and I recommend, submitting multiple times so that, if your internet goes out at 9:45 and you haven't submitted anything, it's a 0, right? There's not a whole lot we can do about that without getting into a lot of logistics. If you uploaded, at 9:30, you've got most of the work there, and I can look at it and say, okay, you were making good progress, and yeah, there was an internet outage, and so okay, we'll take what you did and grade it based on that or something maybe. So make sure your upload is available before the deadline. Canvas will not shut down at 9:50 because some people have extended time allowances. So if you decide you're going to upload at 10 o'clock, Canvas will let you do that. Okay, but there's this draconian penalty for late submissions, 10 points per minute, right? That's not intended to be a calculus equation that says, well, I think if I turn it in 2 minutes late, I can get back 25 points. No, I want you to turn it in by 9:50. This is saying if something happens, if you completely lose track of time and you end up turning it in 30 seconds late, you lose 10 points instead of 100 points, right? So it's a sort of stopgap like that. So make sure you turn it in by the deadline. It's closed book. You're allowed notes, 6 double-sided or 12 single-sided pages. Any format, any reasonable size, any content on there that you want. But that's it for resources. You're not allowed to go online. You're not allowed to look at websites. You're obviously not allowed to, talk to other people or text people or things like that. So sort of standard exam conditions. And then as far as topics, so let's go through this. And like I say, I haven't reviewed this yet, so we may edit this. But likely topics. So, digital versus analog, basic concept of, digital logic, Engineering 250. So breaking things into pairs of values, true, false, yes, no, high, low, 1, 0. Versus analog, which was, Engineering CSE 120, where our circuits produce outputs that could be, half a volt or 2.5 volts or whatever. Binary numbers representing integers and binaries, so weighted positional notation is our usual approach. And if you add up the powers of 2, wherever you have a 1, you get a number. But we also talked about negative numbers and the idea of 2's complement. 2's complement does not mean your number is negative. It's a way to write a number that can be positive or negative. And if you write something in 2's complement, if that most significant bit is a 1, it tells you the number is negative. Otherwise, it's 0 or positive. There's other ways we can write binary numbers. One way is signed magnitude. This is what we do in human writing of numbers. We write down the positive value and we put an extra symbol in front, like a dash, to say it's actually negative. We can do that in binary. We can write the binary version of a number and then make that most significant bit a 1 to say it's a negative number. And so you should know, the range of numbers that are represented by a certain number of bits. If you have, 1,000 pieces of art to catalog, how many bits do you need? And we've done this, with state machines most recently. And make sure we're doing a problem with 8-bit numbers in 2's complement, make sure you use all 8 bits. If you try to find what -5 is, well, you can write 5 with 3 bits, 1, 0, 1. But if you are trying to find the 2's complement, write 5 as 0, 0, 0, 0, 0, 1, 0, 1. Write it as an 8-bit number. It will save you from mistakes. Converting between binary, hex, and octal, that's just grouping sets of bits and writing down symbols for them. Converting between decimal and binary, we can do that by trial and error. We can also do it by that repeated division and looking at remainders. And converting from binary to decimal is just adding up powers of 2. Converting from hex to decimal is adding up powers of 16. Octal is powers of 8. We can represent characters in binary using ASCII. We haven't really done anything with that except I think one homework question. But more generally, we can represent different kinds of information using binary numbers, or strings of binary digits, bits. We can represent pictures, that's something like a JPEG. We can represent movies like an MP4 file. We can represent music with a WAV file or an MP3 file. So we can use binary information to store different types of information. And it's just a question of how do we code it. If we're storing an integer, maybe we'll code it in 2's complement, maybe we'll code it in signed magnitude, maybe we'll code it in Nick code, which is some bizarre code we haven't talked about. But it's more or less arbitrary. But there are some ways of coding information that are more common, like JPEG, 2's complement, and so on. Binary arithmetic, so we can do addition. We can do subtraction by pencil and paper, and so on. Let's see, how much work do we need to show? I have a quick trick for converting binary to decimal, but these have no real work to show. I'm wondering what that trick is. So from binary to decimal, I'm guessing you just add up the powers of 2. So I'm going to say for something like that, if you're really positive you got the answer right, I don't need to see that work. If there's no work and the answer is wrong, there's no partial credit. That's the only downside. But if you're sure it's right. Now, if I'm asking you to do 2's complement addition of 2 numbers and then convert the result into decimal, there's got to be some work there. Right? You've got to at least show me the binary version of the number and then show me how you converted it to a negative by using 2's complement notation. Because I'm usually looking to see if you know how to do those conversions and such. We didn't talk about overflow, so overflow is not going to be on the exam. Gray code we didn't really talk about a whole lot. But just know, it's a different way to represent a sequence of integers, and it's this particular ordering where only 1 bit changes as you move from one number to the next. And we use this in the columns and the rows of our K-maps. Binary coded decimal is another way to represent numbers where we basically write down 4 bits for each digit. So if you have a number like 197 in decimal, I would write that in BCD as a 1, followed by a 9, followed by a 7. So a 12-bit number would give me 197. If I add up these powers of 2, I definitely do not get 197. It's a different representation. There's the first digit is a 1, second digit is a 9, third digit is a 7. So that's called BCD, or binary coded decimal. And again, it's just different notations, different representations of information. Alright, circuits, switches. Make sure you know how to wire a switch. 1K pull-up resistor to power, switch connects your input to ground. You'll definitely be drawing a circuit somewhere on the exam with switches, and your switches need to be correct. LEDs, make sure you have a 1K current limiting resistor in series. Make sure your LEDs are oriented correctly and you can connect them to power or ground. Let's simplify some headaches down the road. This is a symbol for ground. This is a symbol for ground. This is a symbol for ground. This is a symbol for 5 volts. This is a symbol for 5 volts. Somewhere in the text, I think, there's some other symbols used for VCC. Don't use those. Or if you use them, you know, throw a label on there to make sure it's clear that this is ground. But I think there's some confusion because sometimes you see a battery represented like this, where this is the positive side and this is the negative side. And don't try to use this as a symbol for 5 volts. This is a universally recognized symbol for ground, but for power, either put down, you know, positive 5 volts or VCC or something like that. Alright, logic gates, ANDs, ORs, NANDs, NORs, XORs, XNORs, 2 input, 3 input, 4 input. We've been playing with lots of different types of gates, and I'm absolutely confident everybody here knows, you know, everything there is to know about what an AND gate does, what an OR gate does, and so on. We can write truth tables to convey the behavior of these gates by showing the input based on the values of the output based on the values of the inputs. And typically a truth table lists all the possible combinations of inputs, and for each combination shows the output. So we spent a lot of time learning how to go from a truth table to an equation to a circuit. And a slightly simpler direction is the analysis. We start with a circuit, we write equations, and then once we have those equations, we can fill out a truth table. So this is the analysis part, this is the synthesis part. Here's what I want the circuit to do. Let's change that truth table into a set of equations, and then we can put down AND gates and inverters and so on to design a circuit. System diagrams, 40,000 foot view. It's a rectangle with arrows. And the key point is the arrows need to be labeled, and you need a description of what the values on those arrows mean. What does a 0 mean? What does a 1 mean? Or what do these 5 arrows, these 5 inputs mean together? I don't think we did any theorem proving. So I'll say that's not on the exam. But, you know, if you want to prove that De Morgan's theorem is true, you can make a truth table of A and B, and you can show in that truth table what not A and not B is, and you can show in the truth table what not A or B is, and you can say, hey, those 2 columns are always the same. I guess these 2 expressions are the same as each other. But we didn't actually do that, so don't worry about that. Sum of product of sums. Alright, so there's a full form, which is the all written out form. So for example, you know, F equals A bar B C bar, or A B C bar, or B C. Right? That's the canonical form, or the full form, or the all written out form. Right? There's also a compact form, which would be like F equals sum of 2, 3, 6. And I will probably ask you to write out, you know, the full expression for a sum of product or product of sums, and there'll probably be places where I ask you to do a compact form. And there's this MD that pops up for don't cares. So if we have a compact form, we say MD parentheses 2, 4. It means terms 2 and 4 are don't cares. And this comes into min terms and max terms. So these are product terms, these are sum terms that make up the sum of products or the product of sums. Minimization, we can do some minimization algebraically, but the way we concentrated on was K-maps. So let me put algebraically inside parentheses. But you know, you can apply De Morgan's rule to an expression, or you can say A and not A is the same as 0, and so on. But mostly we used K-maps. And so K-maps, right, we for a product of sums, we cover the zeros. For a sum of products, we cover the ones. So write in the ones and the don't cares, and then try to cover the ones, optionally cover the don't cares, wrap around on the edges, wrap around on the corners, and try to get the fewest number of the largest rectangles possible. And then you write an expression from those rectangles. And if you get a checkerboard, you're probably looking at an XOR. And so this is not a sum of products, product of sums, but it could be a way to make an equation or a circuit that is simpler than a sum of product or product of sums. NANDs and NORs are computationally complete, so we can build any circuit using just NANDs or just NORs. Those are really painful questions to grade, so good likelihood you're not going to see a question like that. But I could ask you a question about this, like, you know, true or false, that kind of thing. Multiplexers, demultiplexers, priority encoders, 7-segment decoders. We played with all of this stuff. We did some of it recently in the last Verilog homework, so refresh your memory on those. But, you know, multiplexers will take multiple inputs and choose which one to send to an output. Demultiplexers will take an input and choose which output to send it to. And we saw some tricks with multiplexers, like building big multiplexers out of small ones, or using a multiplexer to implement general purpose logic. Programmable logic, so PALs, PLAs, and PROMs. And these differ in which part of the AND OR plane is programmable. So if both AND and OR planes are programmable, it's a PLA. If just the AND, it's a PAL. If just the OR, it's a PROM. And we've made fuse maps and homeworks and such that let us take a circuit that we want to implement and describe it as a fuse map. And then half adder, full adders, so you should know what these mean, what the inputs and outputs are, what the truth tables would look like, and you know, you've built these from the ground up in a previous lab, so that should be familiar. So that's all kind of the first half of the course. And post midterm material, so we moved from combinational to sequential circuits. So circuits that have a memory. We talked about propagation delays, the fact that circuits don't change instantaneously. And 2 days ago we used Verilog to artificially introduce a delay in our logic blocks and expose a glitch in a circuit that should always output a 0. And we saw in some cases the output can temporarily go high. That's a glitch. So propagation delays, timing diagrams, glitches, those all go together. I use the term latch or gate when we first started talking about ways to store information. And a D-latch was typically a pair of cross-coupled NOR gates or NAND gates. And the idea was there was a gate input, and if the gate was high, then whatever you fed into the circuit would be remembered. When the gate went low, the last value that was sent in is saved in the memory. And that's a level triggered device. And we used that when we started talking about memories, but we said level triggered devices aren't very useful for building things like computers. Because the question is, how long should I leave that gate open so that I have enough time for the input to become valid, but not enough time for the new output of the gate to change that input. So we moved to edge-triggered devices. This is where our clock came in. And the quintessential example of where we need an edge-triggered device was a shift register. So if we have a series of 4 blocks, and the output of one feeds the input of the next, and we have a gate that, you know, whenever this input's a 1, this gets copied to that, and when this is a 0, this is ignored. Well, if these are those kinds of gates, as soon as we set all these inputs to 1, this input goes into here and comes out here and goes into there and comes out here and goes into here and comes out there, and it's run all the way through all 4 of our gates. And so if we wanted to load this into one of these gates and have this go into here and basically shift everything down, the trick would be to set the gates equal to 1 just long enough for these bits to move through one block and then bring the gate back down to 0. And there's this timing issue of how long should I leave the gate high. If I leave it high for too long, my input might go through 3 of these. If I don't leave it in high enough, my input might not even get loaded into 1. And we can't build circuits when we have to deal with this kind of timing. So we change these to be edge triggered. And now it does not matter how long this clock is, because everything happens at the edge, in this case at the positive edge. And at that moment when the clock ticks, that's when this takes its input and loads it in, and this takes its input and loads it in. And since all of those happen at the same time, this input goes into here, the value that was here moves there, and so on. Everything shifts one spot. So the shift register is kind of the motivating example for why we want these edge-triggered behaviors instead of level-triggered. And when we go to an edge-triggered device, that's what we were calling a flip-flop. So flip-flops, we talked about different types, mostly D, JK, and T. So D just copies the input to the output. T has the potential to toggle the output. And JK is kind of like an SR latch. We can either set, reset, or toggle the output based on the values of J and K. We looked at setup and hold time. Setup is the minimum time you have to keep the input stable before the clock ticks. And hold is how long you have to hold those inputs after the clock tick. So you can't change the input at the same moment that you're changing the clock. You have to change the input, wait a little while, that's the setup time, tick the clock, wait a little while longer, that's the hold time, and then you can do whatever you want. And so having non-zero setup and hold times means that there's a limit to how fast we can clock our circuit. And so we can figure out the maximum clocking speed of a circuit. Flip-flops can have preset inputs which set them to 1, clear inputs which clear them to 0. Those inputs could be asynchronous, meaning as soon as we hit the preset line, the output changes. Or they could be synchronous, meaning as soon as the preset is a 1 and the clock ticks, then the output will get set or cleared. So synchronous, these have no effect until a clock tick. Asynchronous, they happen independent of the clock. And more generally, synchronous versus asynchronous logic. Most of what we've done in this second half of the course has been synchronous logic. We have a clock, and really nothing changes flip-flop-wise until the clock ticks. And so that led us to talk about finite state machines. And the basic setup was there were two pieces. There was a memory, which was a set of flip-flops that stored the state of the system. And then there was some sort of combinational logic, which would take a set of inputs and the current state and figure out what the outputs are and what the new state should be. And the output of that combinational logic feeds back into the inputs of the flip-flops, but does not do anything until the clock ticks, because these are flip-flops. So that's your basic setup for a state machine, and looking at the propagation delay of that combinational logic and the setup and hold times, we can find the maximum clock frequency for a state machine. And we did that in the homework. And then state diagrams. These are the pictures with circles and arrows that basically give us a visual representation of how the system changes from state to state based on inputs, and also tells us what the outputs are. And this is where we have to know the difference between a Mealy and a Moore machine. So a Moore machine, the outputs only depend on the state. And since the outputs are just a function of the state, we can write the outputs inside each of those circles, because each circle corresponds to a state. But a Mealy machine, there are some states where your output could change based on the input. So I'm in state 2, but sometimes my output is a 1, sometimes it's a 0. It depends on this X input. That's a Mealy machine. And in that case, we draw the outputs on the arrows coming out of the state. And then we spent, probably 3+ weeks on these two subjects, analysis and synthesis of state machines. So analysis, we start with a circuit, and from that we construct a present state, next state table. So we start with a circuit, we write equations for flip-flop inputs, we fill out a table showing, present state, inputs, next states, outputs, and then we draw a state diagram from that. The synthesis direction, we start with a state diagram. We convert that into a present state, next state table. We figure out equations for what the inputs to our flip-flop should be in order to create the desired next states. We do our K-maps or whatever we're going to do to simplify our equations and come up with these simplified equations, and then we write a circuit. to implement those equations. And of note is that if we are designing a state machine, right, synthesizing a machine using JK flip-flops, it's really important that we take into consideration the don't cares. So if a JK flip-flop is currently outputting a 0, and we want it to output a 1, we have two ways to do that. We could set JK to 1, 0, because that means set the output to a 1. Or we could set it to 1, 1, because that means toggle the output. And since it's currently a 0, toggling will make it a 1. So we can set JK to 1, 0 or 1, 1. That means all we have to do is set J to 1. We don't care what the value of K is. So when we did this with JK flip-flops, we had lots of don't cares. And don't cares are really nice. Why? Because they help you simplify your K-maps. Because they give us more things that we are allowed to cover but not required to cover. And so we may be able to take, something in our K-map that would normally need a rectangle like this, and we may be able to actually cover it, in a single rectangle if we had a don't care right here. So that's the main reason JKs are like so nice when we're synthesizing. And then the last thing that we did was Verilog, basically. And I've got, several lines here, not because this is, a quarter of the exam. You'll probably see one Verilog question. But, this is the thing we've just finished talking about today, so I've got lots of detail here. But, basic concepts of a hardware definition language versus a programming language. By the way, on the lab, I saw a lot of really, really good discussion under lessons learned. A lot of people did some digging into HDLs and Verilog, and in some cases VHDL, and kind of looked at, sort of where this is in the industry right now, and how we got here, and what the general impression is of this, and so on. So a lot of really good stuff in the lab around that. So, the idea of an HDL versus a programming language, we've talked about this. A lot of people reflected on this in the labs, so that's a key concept. The module statement that begins our circuit definition, and so we put ports in there, inputs and outputs. For combinational logic, we mainly use an assign statement, and a really useful thing to do in there is this ternary operator, condition, question mark, true value, colon, false value. For sequential circuit, we usually use an always block, and so we can say always at, for example, positive edge clock, negative edge clock, and so on. And inside our always blocks, we want to use these non-blocking assignments that let us say, take this thing on the right and copy it into the thing on the left at the moment when this always block fires. And then, registers versus wires. Registers usually mean flip-flops, so they remember their value, and so things inside our always block will usually be registers. Things we do with an assign statement will often be wires, but they could be registers also. And, basic syntax, if, then, else, the begin and end and all of that kind of stuff. I'm not going to go super heavy on syntax issues there, but, mostly overarching themes, low-hanging fruit. That's it. That's the course. That's Engineering 250. So I will save this updated content list. And again, lab hours tonight, office hours Thursday morning, office hours Friday morning. If you've got any other questions, definitely come by and ask. Life is getting very hectic this week, so email response time is going to be dropping, possibly dropping out completely. So take advantage of those hours. If you absolutely cannot make it to those hours, it's possible sometimes to make other arrangements, but not Sunday night, right? So, I'll try to work with you within reason, but, all my classes are ending, all my exams are coming up, all my assignments are coming in, so timing is getting trickier and trickier. That's pretty much it. For a Verilog question, I assume we will be handwriting the code for it correct, or would you like us to use active HDL? You are not allowed to use active HDL. That would count as an additional resource, so yeah, write this stuff out by hand. And like I say, if it's quick and dirty, if you don't need to put that, backtick time scale, 1 nanosecond, 1 picosecond, that kind of stuff. I just want to see mainly the module statement. and the code inside there. So put down enough to convince me that you know how to write the Verilog code for this, and you're good to go. All right, that's all I got. If I don't see you before Monday, have a great rest of the week, great weekend. Um, go over your homeworks and your labs mainly to prepare for this. Work out your homework problems, look at the solved problems, rework the problems you weren't sure about. Be absolutely sure you've gone back and read my feedback on your homework questions, because if you're missing some concept, I'll usually put some note in your Canvas area saying, hey, it looks like you're doing this, but it's actually this other thing you should be doing, right? So make sure you look at those, ask questions if you don't understand the feedback. And if you're good on the homework, you're good on the labs, you're good on the basic concepts from lecture, you should be fine on the exam. So I'm not planning any surprises or things like that. All right, have a good one, and I will see everybody next time. Take care, and thanks.